Welcome to this explainer. I'm your host, and today we're stepping into the mind of a Cambridge examiner. We are going to engineer the perfect DNA of an answer for one of the most notoriously tricky topics in A-level physics: energy in simple harmonic motion. We're unpacking the elegant mathematical story of balance within an oscillating system. But we aren't just going to memorize formulas today, no. We're going to break down the evidence and the analysis you need to secure that A-star. By the end of this explainer, you won't just understand the physics conceptually, you'll know exactly how to structure your mathematical proof so the examiner has absolutely no choice but to give you full marks. Okay, let's dive right into this. I want you to visualize a physical object. Think of a heavy mass suspended on a steel spring, or a pendulum on a grandfather clock swinging back and forth, back and forth. Now, pause that image in your head. What is actually happening to its energy at any given microscopic fraction of a second? To truly master this for your exams, and I mean really master it, we need to explicitly track the transformation of energy. We have to map it from the exact moment the mass whips through its equilibrium position all the way out to the very edges of its amplitude, where it momentarily freezes in space. Examiners love to test your understanding of this continuous transfer. Here is our strategic roadmap for today's session. First up, we'll decode kinetic energy and simple harmonic motion. Then, we look at the invisible restoring force. Third, we map out potential energy. Fourth, we combine them to prove total energy conservation. Fifth, we analyze the energy variations graphically. And finally, we will tackle a live, worked example, avoiding the common traps that cost students marks. Section 1. Kinetic energy in simple harmonic motion. Let's introduce the first protagonist of our equation story. Let's move to the derivation and see how this logically builds. You know, some students, let's call them the Alex archetype, they try to just overload their exam papers with raw physics facts, but provide zero analysis of how formulas connect. We're not going to do that. We start with our fundamental baseline. We know that the velocity, v, of a particle in simple harmonic motion equals plus or minus omega multiplied by the square root of the amplitude squared minus the displacement squared. In symbols, that's x naught squared minus x squared. Now, if you're asked to find the kinetic energy, Ek, of a particle of mass m, you simply grab the standard kinetic energy formula you've known for years, 1/2 mv squared. Now we substitute our SHM velocity expression right into that. When you square the velocity, the square root completely vanishes, and so does the plus-minus sign. This beautifully and cleanly yields our target equation. Kinetic energy equals 1/2 m omega squared times the quantity x naught squared minus x squared. Notice how the math tells a story. When displacement x equals the amplitude x naught, the term becomes zero, meaning kinetic energy is zero at the edges. Perfect. Now, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 2, the restoring force. Now we have to transition to the invisible force that constantly dictates this entire motion. You absolutely cannot fully explain simple harmonic motion without rigorously defining this restoring force. This is where rushed students drop easy marks. Let's build the evidence. We know from Newton's second law that force equals mass times acceleration, F equals ma. We also know the absolute hallmark gold standard definition of simple harmonic motion. Acceleration, A, equals negative omega squared times displacement x. So what happens when we substitute this acceleration into Newton's law? We get our restoring force at any given displacement x. F-res equals negative m omega squared x. I need you to look very closely at that negative sign. Do not ignore it. That negative sign is the literal core of the physics here. It proves analytically that the force is always, without fail, directed oppositely to the displacement. It's the universe's way of pulling the mass back to the center equilibrium. If an exam question asks you to define SHM forces, and you omit that minus sign, you've lost the mark. We have to lock down this restoring force accurately, because it is the essential stepping stone to calculating our potential energy. Section 3. Potential energy in simple harmonic motion. Let's look at the second form of energy in our system. Potential energy is the energy that quietly builds up as the particle is forced further and further away from its resting point, fighting against that restoring force we just talked about. To bridge the conceptual gap between force and energy, we have to talk about work. Remember, the change in potential energy of the particle is exactly equal to the work done against the restoring force. Now, basic physics tells us that work done is force times distance. But here is the massive Cambridge exam trap. In simple harmonic motion, the force is not a constant number. Because the restoring force is directly proportional to displacement, it changes every single millimeter the mass moves. Therefore, you cannot simply multiply the maximum force by the distance. That will give you the wrong answer. Instead, you must analyze the system and take the average value of the restoring force during this displacement. This is a crucial piece of analysis you must show in your derivations. And this brilliantly illustrates the elegance of the mathematics behind the physics. Because the restoring force increases perfectly linearly, starting from exactly 0 at the center equilibrium, all the way up to m omega squared x at displacement x, the average force is simply half of that maximum value. So our average force is 1/2 m omega squared x. To finally get the potential energy, EP, we take this average restoring force and multiply it by the total displacement x. That x multiplied by another x gives us x squared. So our beautiful final derived formula becomes potential energy equals 1/2 m omega squared x squared. If you lay your paragraph out exactly like this in an exam, point, evidence, explanation, link, you are guaranteeing yourself top marks. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's put these two energies side by side and do some real analysis. Think of them as a cosmic seesaw. Kinetic energy peaks at 0 displacement. That's right in the middle, at equilibrium, where the mass is tearing through space at its absolute maximum velocity. Potential energy, on the other hand, peaks at maximum displacement, which we call the amplitude. This is the exact moment the particle briefly freezes and stops before reversing its direction. They are perfect, synchronized opposites. When one energy tank is completely depleted, the other is at its absolute maximum capacity. It's a continuous, flawless exchange back and forth. Understanding this interplay is the secret to decoding complex exam questions. Section 4, Total Energy Conservation. This is where the magic happens. We are now going to combine our two equations to reveal the profound underlying truth of the harmonic system. What's really mathematically satisfying here, and what examiners love to see you prove, is that total energy, E tot, is just the sum of kinetic and potential energy. So let's add them up. We take our kinetic energy, 1/2 m omega squared, times the quantity x naught squared minus x squared. And we add our potential energy, 1/2 m omega squared x squared. If you expand the bracket in that first term, you generate a negative 1/2 m omega squared x squared term. And look at what happens next. That negative term perfectly, beautifully cancels out the positive potential energy term. The changing displacement variable, the x squared, completely evaporates from our equation. It just vanishes. We are left with a beautifully simple final equation. Total energy equals 1/2 m omega squared x naught squared. The source text summarizes this mathematical triumph with a really powerful quote. This total energy is constant since m, omega, and x naught are all constant. We might have expected this result as it merely expresses the law of conservation of energy. I want you to really process that. The math we just did isn't just a collection of abstract algebra symbols to memorize. It is a rigorous mathematical proof of a fundamental rule of the universe. Because the mass of the object, the angular frequency of the oscillation, and the maximum amplitude are all fixed constants in an undamped system, the total energy has absolutely no choice but to remain constant. It perfectly demonstrates the conservation of energy. If you can explain this concept in your exam, you are operating at an A-star level. Section 5, Simple Harmonic Motion Energy Variations. Let's look at the data visually. Examiners frequently ask you to sketch these energy variations against displacement. So we need to mentalize this graph perfectly. Picture a standard coordinate plane. First, the kinetic energy. Because of the negative x squared in its expanded formula, it forms a downward-facing U shape, a parabola that peaks directly in the center, y-axis, at 0 displacement, and gracefully curves down to hit 0 at the outer edges of the amplitude. Next, the potential energy. This is a positive x squared relationship, so it forms an upward-facing parabola, exactly like a bowl. It sits at 0 in the dead center and curves up to peak at the edges. Now here is the ultimate test of your understanding. If you take a vertical slice anywhere on this graph, at any displacement point whatsoever, and you physically sum the height of the kinetic curve and the potential curve, they will always add up to the exact same value. Therefore, the total energy forms a perfectly flat, constant horizontal line straight across the top of the graph, connecting the peaks of the two parabolas. Know the shapes, know the intersections, know the system. Section 6. Solving the worked example. It's time for our interactive workshop. Let's put this theory into practice. Let's look at worked example 17b. Imagine a 60-second timer is ticking down. First step, Data scan. We need to extract the core knowns. The mass, m, is 95 grams. The angular frequency, omega, is 12.5 radians per second. The amplitude, x0, is 16 millimeters. Okay, pause. Stop right there. Spot the flaw. What is the immediate trap an examiner has set for you here? It's the units. Students who rush, the ones who miss command word requirements, will plug 95 and 16 straight into their calculators and wonder why they failed the paper. You must convert to standard SI base units before you do any math. Mass must be converted to kilograms, 0.095 kilograms. Amplitude must be converted to meters, 0.016 meters. If you don't engineer your units correctly from line 1, your entire downstream analysis is fundamentally flawed, and you will lose the marks. Now for the actual challenge. Part 1 asks us to calculate the total energy. Part 2 asks us to calculate the specific kinetic and potential energies at half amplitude, meaning a displacement x of 8.0 millimeters, which we immediately convert in our heads to 0.008 meters. For Part 1, we pull out our beautifully derived total energy formula. E tot equals 1/2 m omega squared x naught squared. We carefully plug in our correctly converted SI numbers, 1/2 times 0.095 times 12.5 squared times 0.016 squared. For Part 2, we use our specific kinetic and potential energy formulas, plugging in 0.008 meters for x. And the brilliant part? Once you calculate the kinetic and potential energies for Part 2, you can add them together. If they don't exactly equal your answer from Part 1, you know instantly you've made a calculation error and you can fix it before the exam ends. That is the power of understanding the whole system. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. We've thoroughly mastered the mathematics of simple harmonic motion today. We've seen firsthand how kinetic and potential energy perfectly balance each other in an intricate, continuous dance. Knowing that the total energy of these isolated, undamped systems must always remain perfectly constant, how will you apply these conservation laws to bulletproof your own calculations in the exam hall? Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Take these constant truths, apply them methodically, and I'll see you in the next explainer.